because the initializations and the if statement at the end of each happen only once, no matter how many items there are on the list, and there are about the same number of steps in both linear search and binary search, we're going to ignore these in our analysis. In linear search, then, we figured there were roughly 2 steps per iteration. And in binary search, there were roughly 4 steps per iteration. We're going to compare these algorithms in the worst case. That happens when the value is not in the list for linear search. As an example for linear search, if my list is 1, 2, 3, 4, 5, so there were 5 items in the list, and I'm looking for value maybe 6, then I look here, 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 and here, and then I'm done. So that looked at all 5 items. Let's make a table of the number of items and the number of iterations. If there's 1 item, then there's 1 iteration. If there's 2 items, there's 2 iterations. In general, if there are k items, there are k iterations. And now for binary search. If there is 1 item, then on the first iteration, we set m, we do a comparison, we move either b or e, and then the loop terminates. Let's start building our table. If there's 1 item, then there's 1 iteration. If there are 2 items, then we're going to throw away 1/2 the first time through the loop, leaving us with 1 item, and we know how many steps that's going to take. So if there are 2 items, it takes us 2 iterations. Here's where things start to get kind of interesting. I'm actually going to skip 3 and go right to 4. If I have 4 items in my list, then in one comparison I'm throwing away about half, and that means that I end up with a 2-item list. Well, it took me 1 step to get to this point, so that means that I just have 1 more iteration than I had when I had 2 items in my list. This means that I can process twice as many items with just 1 more iteration. Using this knowledge, let's fill in a few more rows of the table. 8's twice 4, 16 is twice 8, 32 is twice 16, 64 is twice 32, and 128 is twice 64. With 128 values, we can find the index of v in this list in only 8 iterations. Linear search would take 128. Let's plot this on a graph. Our axes are the size of the list, or the number of items, and the number of iterations. If the list has 1 item in it, then there is 1 iteration. 2 items, 2 iterations. 4 items, 3 iterations. 8 items, and 4 iterations. When we double the size of the list, we increment the number of iterations by 1. So thinking about this backwards, if I have 128 items in my list, then after 1 comparison, 1 iteration of binary search, I end up with only 64 items left to consider. When I have 64 items left to consider, then in 1 iteration, I'm throwing away half of them so that after that iteration, I only have 32 items to consider, and so on. This is awfully powerful. Mathematicians have a name for this function. It's called the logarithm base 2 of the number of items. Here's one more way to think about logarithms. It's the number of times you can divide by 2 in order to reach 1. So, how many times can I divide by 2 in order to reach 1? Once. What about 4? I can divide 4 by 2 to get 2, and 2 by 2 to get 1. That was 2 divides. 8 is going to be 1 division by 2 to get 4. 4 divided by 2 is 2. 2 divided by 2 is 1, so that gives us 3 divisions. 16 is 4 divisions. 32 is 5 divisions, and so on. So let's try to calculate the logarithm of 1024. Well, 1024 is 512 times 2. When we divide 512 by 2, we get 256, then 128, then 64, then 32, then 16, then 8, then 4, then 2, and then 1. So there's 1 division, 2, 3 divisions, 4 divisions, 5 divisions, 6 divisions, 7 divisions, 8 divisions, 9 divisions, 10 divisions. So the log base 2 of 1024 is going to produce, what did I say? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.